Hello? Hello? Hi, I'm Arnav, and I'm going to be talking about implementing hybrid resource analysis in resource-aware ML2. So, resource-aware ML, or RAML, is a tool for automatically deriving cost bounds on programs. The notion of cost is user-defined, so it could mean time, energy, heap space, stack depth, and so on. RAML's bounds are multivariate polynomials in the input size and are necessarily sound, which means that they're valid for any possible input to the program. So let's say the user is interested in bounding the number of function calls performed by mergesort. They would annotate the program with the tick cost annotation construct, which would be incremented whenever you enter the body of mergesort. If you ask RAML for a bound on this program, it'll give you a concrete quadratic polynomial, which is sound but is noticeably loose. And this is kind of unavoidable because RAML is incapable of expressing logarithmic bounds. That is, it is sound but incomplete. Dually, data-driven analyses are capable of deriving tight bounds on more programs but are necessarily unsound. Thus, the point of hybrid resource analysis is to combine these complementary strengths and weaknesses. One such method is resource decomposition, which is a step-by-step process to derive tight bounds on programs that RAML struggles on. And we'll see an example through mergesort. So in mergesort, we must first identify the semantic property that RAML struggles to bound tightly. For mergesort, this is its recursion depth. We call this semantic property a resource component, and for my purposes, this will always be the recursion depth of some function. The next step for the user is to define this semantic property using the mark cost annotation construct. In the case of mergesort, mark is incremented whenever you enter the body of mergesort and decremented whenever you leave the body of mergesort, which corresponds to tracking the recursion depth. This program is termed resource decomposed. Then we transform the resource decomposed program into one which takes an additional natural number parameter. This parameter is a ghost variable representing the worst case recursion depth of the program. So before we do any computation, we check whether the recursion depth is 0 or not. If it is, then we raise an exception, which means we incur no further cost. Else we use the decremented recursion depth for the recursive calls. Such programs are termed resource guarded. Finally, we solicit RAML for a bound on the resource guarded program, which gives us a multivariate bound in terms of the list length as well as the recursion depth. Finally, we can use a data-driven analysis to derive a logarithmic bound on the recursion depth and then substitute it into the resource-guarded program's bound to derive our final O of n log n bound on mergesort. So what I do is I implement resource decomposition as a largely automated process in RAML2, which is under active development as an improvement to RAML. At a high level, the architecture is as follows. At the top level, we have a resource decomposed program, which treats the recursion depths of a number of functions as resource components, which we will call R sub 1 through R sub m. Then I implement an automatic program transformation, which converts this resource decomposed program into the resource guarded program, which takes additional parameters R sub 1 through R sub m, one ghost variable for each resource component. Finally, we use RAML2's own static cost analysis to derive a sound cost bound on the resource guarded program in terms of the original input x and the newly introduced ghost parameters R sub 1 through R sub m. Now, when doing this program transformation, we want to think of mark as a resource effect and all expressions that may use it as resource effectful. Resource decomposed programs do not make a type distinction between pure and effectful expressions. As you see, mark just has the type unit. Thus, the first step in the transformation is to introduce the monadic type f of tau, which represents resource effectful expressions which may return a value of type tau. Then we lift all resource effectful expressions into this monadic type. Once mark now has the type f of unit, for example. Once this type distinction is introduced, we can complete the program transformation by a type-directed transformation. And the transformation is basically going to interpret every expression of type f of tau as a function which takes the current state of the resource components, sigma, which is a tuple of natural numbers, and gives you back the updated state of the resource components, as well as the transformed value. Independently, we run our data-driven analysis, which proceeds by running the program on a finite set of generated inputs, as well as logging the peak recursion depth of each function at runtime. This induces a cost dataset which we can then analyze via the existing data-driven analysis model to derive a linear or logarithmic univariate bound on each resource component. Once that's done, we can compose the two bounds to report our final composed bound. So for the evaluation, we choose a number of common functional programs which contain one or more functions with logarithmic recursion depth. And we run the data-driven analysis with 200 randomly generated samples. And on each of them, we are able to derive a tight bound that happens to be sound. For future work, we intend to enable the program transformation to support non-local control flow so that we can account for exception handlers in the source IR. Thank you.
Thank you. Questions?
Hi, great talk. I just wanted to ask whether you have an example in mind for, say, a data structure or an algorithm where you think that RAML2 wouldn't be able to give a tight bound. Like, is there something logarithmic where you think it wouldn't be able to get a tight bound?
No. If it involves a logarithm in the ground truth complexity, RAML is guaranteed to give you a loose bound because it's incapable of expressing logarithmic bounds. Its bounds are always going to be polynomials.
But is there any data structure that has a logarithmic, say, type bound where RAML2 won't get that type bound?
A data structure?
Or like a type of tree or something like that?
So red-black trees have logarithmic operations, so do leftist heaps, and each of them has like an efficient function I mean, those data structures are efficient because they have a logarithmic recursion depth function out there in their implementation, and RAML is guaranteed to give you a loose bound on their complexity.
Okay.
He's asking about your work, like RAML2,
Oh, RAML.
Yeah.
Oh, sorry. So, you mean RAML2 with resource decomposition?
Yes, yes.
Oh, sorry, my bad. Yes. In fact, in my evaluation, I do test it against a red-black tree example, and that example is basically just taking a list of keys, adding them all into a red-black tree, and then removing them, and then taking a separate list of queries, and then querying the red-black tree. So that bound you see, that tight bound you see that we derive, is with resource decomposition in RAML2.
Okay.
Yeah, sorry, I misunderstood your question.
So basically you're saying that you expect that complex trees with logarithmic bounds, RAML2 will get a tight bound.
Tight, not necessarily sound.
Thank you.
Other questions?
Thanks for the really nice presentation. So you mentioned that this sort of resource decomposition technique is an existing technique. Can you say a bit about what aspects are sort of being developed now as you try to integrate it into RAML2, or like are there new challenges that have come up that weren't part of previous implementations of this technique?
Yeah, so there are like two broad things. Firstly, the program transformation in the original, like there was a paper last year, I forget if it was PLDI or Uppsala, but the program transformation was manual. In this work, I automate that. And another thing was that in their data-driven analysis, they were only focusing on like specialized types like lists and graphs. Here, my implementation accounts for arbitrary inductive types. So the generator is able to like, so in the data-driven analysis, it proceeds by like running the program on a bunch of inputs, and that input can be any inductive type. That's the other contribution.
Other questions? Yeah.
Yeah, thank you for the talk. I guess I'll follow up on the first question. So is there any example, maybe not involving logs, but where that you tried and that your techniques did not work? So you didn't get a very good bound.
Like RAML2 with resource decomposition didn't give you a good bound? No, I have not tried it, but I expect you can get asymptotically unsound bounds if you try resource decomposition with on RAML2 with functions which have like square root n complexity. So there are some efficient algorithms which happen to have square root n recursion depth. And using those algorithms, you can kind of fool the data-driven analysis into thinking that it's actually logarithmic, but in fact, it's square root n.
So let's assume that the data-driven analysis is correct and gives us the sound answer. Is there any example where the result is not precise? Like it's, I'm asking about precision, not soundness. Examples that you've tried. You know, any example program that you've run.
I have not run such an example, but I can tell you how you can produce such an example.
Okay.
So, I mean, let's just say you just, one thing the user has to do is that they themselves have to insert these mark annotations, which means they need to use their domain knowledge in order to like figure out which functions will actually have loose bounds with RAML. Now, if the user happens to not use this domain knowledge and forgets to actually include these mark annotations, then the recursion depth of that function will be bounded by RAML, and we know that that's going to be loose. So sure, you can like just forget to put marks, and then even resource decomposition might give you asymptotically loose bounds.
Okay, makes sense. Thanks.
All right, let's thank the speaker again, and that concludes our